Well, yeah, thank you so much for having me. And I am really grateful that you allowed me to push back a week. Somehow I managed to get pneumonia in the middle of August. So, special award for that. I don't know. But so anyway, I appreciate you taking the time for that. This talk really was born out of SPIE this summer. So I met Jennifer at SPI this past summer, and she was giving a talk about the EPRV group and the goals of how we want to try to start limiting some of the systematics so that we can really get these Earth-like analogs out of our data. And so one of the things she talked about is, that she wanted to start comparing bits and pieces of pipelines in some very controlled way so that we would be able to come up with effectively like some, main pipeline that the community could kind of say, okay, this is our baseline. And then if you want to make improvements on any of these steps, this is the canonical metric you measure against. And so I caught up with her afterwards and I started talking. I said, we've actually done a lot of the framework code to be able to do this. And so that's what I want to tell you a little bit about today. So my title is BANZAI-NRES, a modular pipeline framework to measure radial velocities. And so I've got Las Cumbres Observatory on here. I've got BANZAI, I've got NRES. So I'll give you a quick overview of those real quick. And then I can talk about a little bit more detail, some of the nuts and bolts of how the code is structured and how I imagine that we could start using it to improve the existing radial velocity pipelines and set up some kind of canonical metric to compare some of these different reduction steps. So first, bonsai. Bonsai is not named after the tree, even though I get asked that sometimes. It's actually more named about the pipeline, the surf pipeline. I'm pretty sure that this guy in the middle is me. I'm generally waiting for all of the water to come crashing down on my head. So anyway, that's where the backronym comes from, but I'll show you a little bit more about that in a second. All right, so first, what is Las Cumbres Observatory? Marshall will enjoy this, especially because this is the token slide we have to show at every Las Cumbres talk just to tell people who we are. Las Cumbres Observatory operates a network of 25 robotic telescopes around the world. In general, we're small aperture telescopes, so mostly 1 meters and 40 centimeter telescopes. The 1 meter telescopes are really our workhorse instruments, and we have those, as you can see, around the world. And we have two 2 meters, which have low resolution spectrographs on them. For this talk, I will be focusing on NRES, which are on our 1 meter telescopes. So we have NRES units in Chile, South Africa, outside of Tel Aviv, and then one in McDonald in Texas. NRES stands for the Network of Robotic Echelle Spectrographs, which is a great acronym if you want to make this plural. So I'm not sure if it's NRESs or what, but anyway. So this is comprised of 4 spectrographs, R of about 50,000 on our 1 meter telescopes. And right now, we are achieving on a regular basis 20 meters a second radial velocity precision in a fully automated robotic way. Now, that's a long ways from EPRV, so I'm going to be focusing more on the infrastructure than I am on most of the science results, because we're kind of talking about different regimes. And then BANZAI. BANZAI is the data pipeline framework that has been designed specifically for Las Cumbres Observatory. There's an SPIE paper on it from 2018 if you're interested, but this is the pipeline framework that has to handle all of the data that comes in for the entire network of telescopes. So we have something like 25 imagers, 6 spectrographs, and all of that data has to get funneled through the BANZAI pipeline. And so it has its challenges for sure, but because of just the volume and the heterogeneity of the data that we have to deal with, we've had to modularize the pipeline to make it very plug and play so that it is up all the time and it's not dropping data all the time. We're also at Las Cumbres very specifically focused on time domain astronomy. And so minutes, hours count when you're talking about reductions. This is something that I can't just hand this off to a grad student and say, good luck, see you in 6 months, like reduce me some data. This is something that has to work all the time, and it has to work without or with basically no human interaction in it. Now, that does make for some very interesting new capabilities that we can do. So one of the things is, because we automatically detect data, we have integrated the BANZAI very closely into our telescope operations. And so the way the data model works, at least how we have deployed it, there are other ways that we can do this, but how we have deployed it is our telescopes are at site, unsurprisingly. They take an image, they take a spectrum, the shutter closes, they write to disk. They then broadcast a message via a queue. It's called RabbitMQ if you're interested. That is then picked up by something we have called the shipper. That shipper copies the data into the Amazon cloud. So a lot of our infrastructure is in Amazon. And then once it's in Amazon and available, that broadcasts a message to BANZAI. It's time to process this new data. And then we process it, put the process data back in the archive, and then we send them. Then it's available to users. So that's kind of the data flow diagram of how this works. There's, like I said, there's already interesting things we can talk about that I'm happy to talk in more detail about, like deploying pipelines into the cloud rather than on local machines. If you've ever tried to install, someone else's pipeline onto your local machine, you know how exciting that can be. But also, cloud infrastructure is set up in a fundamentally different way than I think we as astronomers are typically used to thinking. And so because of that, there's a lot of lessons that we've had to learn on how to do this and deploy this to the cloud in a way that is both robust and it doesn't cost $1,000 a day kind of thing and break the bank. And then we've also integrated things very tightly into telescope operations. For example, this panel on the right shows, some diagnostic plots of all the images we've been processing for the night and looking for, a variety of issues or frames that didn't process correctly, or, how old our flat fields are and things like that. And so by doing this in an automated and cloud-based way, it's very natural to be able to integrate this into the rest of our observatory operations. All right, so that's kind of BANZAI in general. What about NRES? So NRES is kind of an interesting echelle because it's not fed by a single fiber or even a fiber and a calibration fiber. It's fed by two different telescopes. And so there are three fibers that feed a single NRES unit. So there's a fiber from telescope 1, a calibration unit fiber in the middle, and then a telescope fiber from number 2, or from telescope number 2. And unfortunately, some of these orders overlap. And so we don't currently operate with both telescopes at the same time. We only operate with one at a time, but it does mean that there's basically two configurations that we have to be able to track as we're processing data. So here on the left, it's got one science fiber illuminated, and then there's the arc features, the little blobs, the little dots are the are the arc lines. Hang on, sorry, I just got a question. Yeah, I can talk to about hopscotch. So Eric Ford asked, have you looked into the subfield of astronomy or dealing with data from multiple instruments? I've heard of hopscotch. So interestingly, hopscotch is built by a group called SIMA, and I am the product owner in SIMA, so I actually am helping lead the development in that. So yes, I've heard of hopscotch for sure. And we could definitely talk about that more in a second. So yeah, so two science fibers, calibration fiber. So we have to be able to handle that in the pipeline. The extraction is done in a standard way. It's done just using optimal weighted extractions. And we take the blaze function out of just a lamp in basically the standard way. So we use thorium argon arcs for our wavelength solution. Something I just want to point out quickly is that for our arc, or for our wavelength solution, we take advantage of an algorithm that one of my students came up with, along with Tim Brandt. He's now in Maryland, I think. And this algorithm allows us to automatically calibrate the initial guess for your echelle spectrograph wavelength solution. And it does this by leveraging that each echelle order overlaps the next one just by a little bit. And so by doing that, you can actually figure out in a fully automated way what your absolute wavelength calibration is with no human intervention. Now, kind of when we started this, a lot of people said, well, you only have to come up with this initial guess once, so it's not that bad. But then, you know, they said they were telling this to me, who's coming up with a wavelength solution, but then we have 4 of them. And then over time, as we have updated things and had to service the instrument and stuff like that, we've had to come up with entirely new ones. And so, yes, while you do it once, that's great. The real issue is that if you do it more than once, it becomes really, really tedious. So this is a fully automated way to figure out your wavelength solution from just first principles. I would say we do okay on our wavelength solution. I would say not fantastic. This is a typical wavelength solution plot. And you can see that there are many lines that we could probably filter out that would then shrink at least our residuals down and hopefully improve our fits just a little bit. Right now, the community demand for NRES has not been asking for the highest quality and the highest level of radial velocity precision. At this point, most people use NRES as kind of a recon type instrument rather than trying to get the final radial velocity. So one thing I actually do want to advertise is that we do have a lot of time, and I would say these instruments are currently underutilized that can be used for say recon spectroscopy before you need to go put a big 8-meter type class telescope on it and try to get a really high precision radial velocity. So I hope that people will be able to use these more. And if you want to talk to somebody else who's had some experience with it, Marshall Johnson was at LCO for a while, and he actually has been very instrumental in putting this pipeline together as well. So he's another good resource to talk to about using NRES for, say, recon spectroscopy. So at the end of the day, here's a real radial velocity curve, and we're finding just of the base star of 51 peg, and our early results show that we're down to 20 meters a second with no human intervention at all. So this is entirely automated end to end. I haven't tweaked any of the data. This is just straight what comes out of the pipe. Fortunately, you see that, and actually one of the nice things is we have overlaid here observations from 2 different sites. And fortunately, neither site seems to stick out too much. And so we think we've done a pretty good job of cross-calibrating the radial velocities from different sites. So that's hopefully working well. Just a few words on talking about getting data to users. So right now we're quite fast in how we do our processing. From shutter close to the availability to users, a fully processed spectrum takes between about 1 minute and 2 minutes. And so this is really nice if you want to do, say, time domain follow-up of sources. Now, this is probably less important if you're doing long baseline monitoring for EPRVs, but it's still just a good number to keep in your head that we're not talking about hours of processing time here. We're really talking about minutes. Another thing we found is that given all of this is automated, we've had to come up with quite a variety of visualizations so that users can validate their data. So this particular one, so for every single one of our spectra, we produce one of these plots. The top should look pretty familiar to people like Dave Latham because it's actually modeled off of a lot of what he's done. And then, a variety of different information about the basic classification of the star as a summary, showing the cross correlation function and the radial velocity and the different levels of signal to noise, just making sure that everything passes muster. Similarly, we can do this with a wavelength solution. We can plot, where do the lines end up, and make sure we trust our wavelength solution. And so I've of course cherry picked one that worked very well. So this lines up well, but there are cases. In the case of a failure, it will look drastically off, and so you'll be able to identify issues in that way. Okay, so that's really all I want to talk about in terms of where we are at this moment in terms of science. What I want to talk now more is about how can we use Bonsai to say start comparing these different pipelines, different analysis algorithms, things like that. So one of the things I want to point out that I think is very important, especially for a field that's trying to push to the level of precision that we are in this EPRV community, is that all of our pipelines are open source. So they are all available on GitHub, and anyone can download them, anyone can use them. And we've designed them, and I'll show you more about that in a little bit, to try to be as instrument agnostic as possible so that it's relatively easy to adapt some of these pieces of infrastructure to work for other instruments. We are an open source project in as much that we haven't just done a code dump, but we also have support here that includes documentation, and it includes continuous integration tests to show that we haven't introduced bugs and regressed the quality of the code. All of the discussion about pull requests is public, even if they're internal pull change requests. And so I really think we need to be as open about this as possible. We've got a standard read the docs type thing. And so if you're interested in starting to look through some of the different documents that we have and you don't want to just go straight to the code, I recommend that you can take a look here. And so it's just banzai-nres.readthedocs.io, and that will get you here. And there, we've tried to cover all of the use cases, or as much of the pipeline questions that we get, but I'm sure there's missing things. So if you find something that you don't know the answer to, that's the other great thing about being open source and me being at this talk, is that I'm very happy to answer questions. Shoot me an email, send me a message on GitHub, anything, and we'll get back to you. Now, you might think that given what I showed you about the cloud infrastructure and all of that, you might think that all of this is just going to be way too heavy-handed, and it's going to be way too much to use on your local machine, that you don't want to set up all the infrastructure. The good part about that is we've actually separated the responsibilities of a lot of the code in several different ways, one of which is the pipeline is perfectly happy to run on your local machine inside a Jupyter notebook in this particular case, with very little setup, and to get you reducing data. Now, it also includes all the cloud infrastructure, all that code is available, but it's not necessary to be able to just start looking and start playing around with the pipeline. So one of the things that we have on here is an example data reduction, and it starts, and it even downloads the data that you're processing as you go. And so, we've given you some list of some file names or something that are all publicly available from Las Cumbres that you can download, and then you can run the pipeline and process it and start looking at kind of the results that you're getting. All right, so now I want to get a little bit more into the nitty-gritty on some of the reasons that I think BANZAI-NRES and Bonsai in general really could be a good tool to start comparing apples to apples on some of these different analysis algorithms. So one of which is that there's no plumbing code necessary. Bonsai is designed to handle all of the plumbing between stages intrinsically. So it separates the responsibility of figuring out how you're going to connect this stage to this stage to this stage, with the actual algorithm reduction logic from itself. So in fact, this is the entirety of the code that is necessary to do our background subtraction stage that you would have to implement. Now, of course, I picked an extra simple one where we've shelled out to a particular library called SEP, which was maintained by Kyle Barbary. It's a Python wrapper to the source extractor background algorithm. But the point is still the same. There's no huge overhead here in writing, lots of code to say, okay, this is where you have to find the file. This is where you have to find the calibration. This is nothing, none of that like that. All of it just comes in, and it's very, very well separated. So you can imagine if you wanted to be able to test a different background subtraction technique, all you'd have to do is implement, okay, I have an image that's going to be processed in some way, and then implement, here's my algorithm to actually subtract the background, and then just kick back the image into the stream, and then you're done. You don't have to put everything else. And once you do that, the whole system is set up to be as plug and play as possible. And so all you want it to do, if you want to say change out how we do any one stage of the processing, is you simply edit this list, and it's just a Python list, and choose a different one. So in fact, here I've taken out background subtraction because it's starting to do bad things with negative fluxes and over subtraction. And so this is a place I would say that still needs more development in BANZAI-NRES. And because, our simplistic background subtractor is not up to snuff. You write a new one, you slot it in, you put it in this list, and it automatically gets thrown into the calibration or into the pipeline. So if you were then comparing pieces of pipelines, say, okay, I want to do a different type of extraction. Well, you simply replace the extraction, and everything else, every other bit of the processing is going to be identical. And so, how the overscan is subtracted, how it's calculated, how, the image is trimmed, how, which dark is used, all this stuff is exactly the same. The only difference is that one individual piece that you have changed, which gives you a really strong, a really good control sample to figure out, to be able to identify which pieces of which pipeline are actually producing the highest quality results. We've also tried to do our best to keep to do maximal code reuse or minimal copy and paste. So anyone who's written a pipeline knows that there's a temptation to copy and paste huge chunks of code that from one function to the other, and then change, the three things about it that you need. And then hopefully that works, and it works for a while. And then you realize that there's a bug in the original one, and you say, oh no. And then you have to find the three places that you copied it, and you have to go edit each of those three places. We've tried to avoid that as much as possible. So one of the things that we provide is the stacker mechanism. And so in a lot of the processing, both imaging and spectroscopy, there's many cases where you want to take n frames and then you want to stack them down to do some kind of average with some kind of outlier rejection. Because that happens so frequently, we wrote our own custom version to do this. We've tried to make it quite fast, so we've put some of it down into this. There's a little bit of Python around, but not much. But the nice part is, say, if I want to go from a bias stacker, so I want to stack bias frames to stack dark frames to stack flat frames, this is the entirety of the code in BANZAI to set up stacking flats. So it's 6 lines. I tell it what calibration type that I want it all to group together. So in this case, lamp flats. And then I tell it this is a stacker stage, good luck. And then I can just go back and I can put that here. So this BANZAI-NRES.flats, that particular part is in a slightly different place, but you put that into the code, into that type of list, and then it'll automatically pick that up with basically no real repeated code. The drawback of this, nothing's free, right, is that we've had to use a pretty liberal amount of inheritance, so object-oriented programming, which is mostly very nice, and it kind of obfuscates a lot of the work that you would have to do and making it a little bit easier. But the downside of the obfuscation is that it's sometimes difficult to find exactly what's going wrong if something is having an issue, some low level thing. We also do an automatic tracking of where the calibration data lives. So BANZAI maintains a database. Now that database can actually be as simple as an SQLite file on your hard drive, or it can be Postgres or MySQL. We wrap something called SQL Alchemy, which abstracts away the exact implementation of the database, and instead we can use it on a variety of different platforms. So if, say, oh, I want to use MySQL because that's my favorite thing, I've used it forever, totally fine. BANZAI can hook up to that. Or if you say, I don't want to go set up my own database server, I just want to do it on this file, there's an SQLite implementation. So that's good. But it also means that when you're talking about applying these different calibrations, you don't have to worry about telling the pipeline to go get it where the file has to live, or anything about the file really in general. Instead, you just have to override this, apply master calibration function, and it's already plumbed through in the back end, figures out how to load it whenever you call this right off the bit. And so I can, again, focus instead of on the plumbing to get the file from one place to another, I can work on what's actually happening. And in this case, it's very, very simple. I'm actually just copying out a lot of the previously determined things out of the lamp stack at this point. So things like, where are the traces? What's the profile of the lamp look like? What's the blaze function? That kind of thing is just getting copied into my image, which I can then use down the line. So this is an exceptionally simple one, but in general, it also allows you to focus on the algorithms and not the plumbing code. As I said before, we've pushed the whole thing to be very not instrument specific, so instrument agnostic. We don't require a certain header structure. We don't require a certain even really data structure. The way we do this is we've abstracted how all of this is stored from telescope to telescope into something called an abstract base class, which is this ABC meta class. And what that allows us to do is, there's some basic functions that we're going to be able to define for anything. Like if I want to get the primary HDU, I'm always going to get that in the same way, so that's fine. So I don't have to repeat the code. But there are also of these other functions, like how do I get the bias level, or how do I get, certain processing metadata that I'm interested, that I want to be able to store. All of that lives in a function that is basically empty. And for any specific case, you have to implement it as you want. And so there's a little bit of code you have to add to basically tell the pipeline where, say, these header keywords live, but it also means that we're not tied to any one particular instrument. So we've got an overall observation frame, but then this is the Las Cumbres specific implementation of this. So say I wanted to figure out what the observation type was. Is it a bias? Is it a flat? Is it a dark? I know, because I help control the data from Las Cumbres, that it's going to live in this obs type keyword. Oh, sorry, that jumped. It lives in this obs type keyword. So that's probably not too strange. But there's some other things, like maybe the night of the observation, which we used to try and decide what we should stack together. And that's in this dayobs keyword, which is a much less standard keyword. And so if you wanted to, say, use this on a different spectrograph, you could then map these to whatever header keywords that you would like for these different ones. We've done something similar in the data. So again, the internal algorithms don't actually want to have to know, oh, the gain keyword is going to be gain. Now, most of the time it's going to be gain, so that's fine. So it's kind of a bad example. The saturate keyword, it's a little bit less. If you want to talk about read noise, that sometimes there's, as you start going down the list of these different keywords, there start to be more and more different iterations between different cameras and different instruments. Now, instead of having to include all of that, we've defined a set of properties inside our data classes so that we can then just call those. So I can say, image.gain, instead of every time having to write image.meta.getGain, with this 1 and 0. And so it's nice shorthand to be able to make the code more readable on what you're actually doing, again, with the goal of making it easier to try and separate the responsibilities of, the plumbing parts of the code with the true algorithm that's happening in the middle. But it also is nice because if somehow all of a sudden my gain keyword gets changed and it's no longer gain, I don't have to go back through and change everything wherever I use that keyword. It's changed in one place and then it's automatically propagated through the rest. We also do an intrinsic propagation of uncertainty. So we add shot noise and read noise and shot noise basically through each of the different processing steps. And we track that through each stage of processing in the pipeline with the goal of making it as accurate of an uncertainty on the final radial velocity as we can produce. Now, again, we've talked about we want this to be as as self-contained as possible. So we've actually overridden some of the internal Python operators for our different data types. So if you say took a observation frame and say observation frame times 3, it's not going to just do that on data, but it's actually going to multiply the data by that value. It's going to scale the uncertainty by that value. It's going to update the saturate keyword so that we know that the saturation is going to be kept track of. It's going to rescale the gain so that you can tell what units your image are in. And then it's going to also do something with max linearity. And so in the code, at the end of the day, you've written, A times B, but there's more going on under the hood. And so for the multiplication, that's pretty mundane, pretty simple. For division, propagation of uncertainty is a little bit more complicated. And so this is the propagation of uncertainty formula here. We also include masking and things like that. So if we divide it by something that has a mask, we want to make sure that we flag that data as suspect. But on this uncertainty propagation here, you could imagine if you wanted to propagate your uncertainty through every time you did this, you would need to write this rather obnoxiously long line every time you did any kind of division to be able to track the uncertainty. Because we do it here, we write it once, and then every time we do division, the uncertainties are automatically propagated. All right, and then, so shifting gears a little bit. So this is how we've developed kind of the internal structure of the code in hopes of making it as applicable as possible. We've also designed a variety of unit tests to check all of these individual components to make sure that they're doing what we want. And the way we've done this is by using mostly synthetic data. And then by using synthetic data, we know the answer, we know the correct answer. And so that we can then check and make sure that whatever we're doing on that individual component is producing the correct result. Now, there's a lot of different things we could talk endlessly about testing, but this is another reason that breaking things into individual stage components is very important, because if I have to say synthesize the entire processing chain of, say, an image or something like that, that's just going to basically be impossible. Instead, if I say, okay, this is what this is going to look like. So for example, here is a set of traces that I put onto a synthetic frame that I know the right answer for. I can then go test that individual block, that individual unit, and I can figure out if my algorithm is doing what I want it to do. So if you want to start comparing algorithms, it's a really good place to start plugging things in and say, okay, this algorithm gets the precision of this fit down to n% with given this noise characteristic or something like that. And then if you want to go test a new algorithm against that, it better at least be that good before you pass it out to production. We also do a full end-to-end continuous integration testing suite on real data. So we use GitHub Actions, which actually spins up a mini Kubernetes cluster and then processes a bunch of data and says, great, all of this produce the right thing. But it also gives us the opportunity to say, okay, here is, this person's by hand reduction that has all the magic in it that makes it, the precision, a 0.1 meters per second or something like that precision. You can include that in your test data, and you can then require that the pipeline, any change to the pipeline doesn't decrease the precision that is produced on that data set. It's also a good chance to do consistent development, or deployment, I'm sorry. If you ever tried to install, again, another pipeline on your machine, you know how that can be fraught with issues. So you can, sometimes it works great. Sometimes it's like, well, it works on my machine, right? That's the classic line. Instead, we have abstracted that into a combination of Docker files and Kubernetes deployment YAMLs to ensure that we always are building on the same versions of everything. You can basically make, for lack of a better analogy, a virtual machine that's exactly the same structure, that's exactly the same versions, and you can consistently test things across without having to make sure that you're actually on the same physical piece of hardware. So they don't have to loan your laptop. So this is what the Docker file looks like. This is what the deployment looks like. It's, it's kind of messy, but it's really nice for, again, making direct comparisons. And we include all of this code as well in a separate folder. So all of, the Python code is in this BANZAI-NRES folder, but then all the deployment code is, under these Helm charts, and then the Docker file is down here. So again, even our deployment is meant to be open and reusable as much as possible. And then I will make a quick plea to say that the world is changing, and we need to get some of our visualization tools up to snuff. So this is, let's see if this plays. There it goes. This is a little web widget I had built that does very, very simple, Gaussian fits to lines. The great part about this is all based in a web browser. So in principle, you could go run this, or I could run it on my local machine. You could go to a website, and then you could just be able to use it right out of the bat. And that's actually what we're working on deploying for our fluids, our low resolution spectrograph, which is kind of a bizarre thing, and I'll show you in just a second. But we're working on that so users can go look at the extraction, see how things are going, and then they can decide if they want to be able to re-extract with, say, a different background region, or a different part of the trace. Say there's two traces, one's a star and one's, your science target, and then we extracted the star automatically. You can then re-choose the extraction region as well. So actually, I'm going to go there right there. And see if that'll play. So this is our Floyd's instrument, which is actually a low resolution 2-order echelle. So it's still an echelle, we'll say that, with a little bit of extra fun in it, as we'll call it. It's got a long slit on it rather than a fiber. And so you have to worry about things like long slit sky subtraction on an echelle, and you can see the nice orders are bent in kind of weird ways. So let me tell you, this data is fun to be working with. And so we're just getting ready to deploy our initial production version of this. But the idea is we built this web interface so that our users, without installing any kind of software, can actually go look at their data. They can interact with their data. What I've been working on recently is you can actually drag these lines up and down, and you can change the extraction regions that are going to show up down below. You can start to question validation. So in this are like question assumptions about the algorithm. You can see that the data is not actually a perfect fit to a Gaussian profile. And so these are the extractions that, as we're going, you'll have a button later that allows you to click, and it updates these plots. And then once you're happy, there's a button to save this to archive. So I think as a community, we need to start developing more of these interactive type tools that can work through something like a web browser that doesn't require a huge amount of installation and setup, but it's still very reactive, even harkening back to the IRAF days and everything kind of in between. So that's where I will leave my part of the discussion. But yeah, I'd love to talk about how we can use some of these things to do direct comparisons between different pipelines. And so we can really start to isolate which algorithms do truly produce the results that we need, and they don't produce the systematics that we're worried about. Systematics are king, right? So we want to be able to make sure that our data processing is not unduly adding systematics that we can't take care of. So we've built this pipeline for ourselves, but I hope it's actually going to be useful for a lot of other people as well. So let's talk, and I appreciate your time.
Great. Thank you so much, Curtis, for that talk. Questions for Curtis, either you can type them into the chat or you can use the raise hand feature on Zoom. Sam, go right ahead.
Hi, Chris. Thanks for that. Very interesting stuff. So I'm all for unit tests at every kind of individual module, I'll call it level. I think there are ways to define, relatively straightforward metrics to kind of test against as you make these little refactorings and improvements. I do think that kind of the long arc of full-scale unit testing on RVs, I think, is a perpetual challenge, right? Because you don't know what to aim for. It's not necessarily only the RMS goes down, although we would prefer it be that be the case. But have you thought about, like, kind of at the time series level, specifically for RVs, to me, it's a data question of like picking the right data products, whether it's solar data or ultra quiet stars, what have you. But have you thought about, in kind of this rolled up sense where you're running all these individual unit tests, what's the right approach for that in this framework?
Yeah, so there's a couple pieces of that. So we actually have two separate tests, or sets of tests, really. We have our unit tests, which do exactly as you say, take little synthetic bits of data and say make sure it passes it through the algorithm, and it's like, okay, it gives us the answer that we put in. We got out what we put in, we're happy, great. You're exactly right that doing the longer term like time series is much more difficult, and so we have this idea of kind of an end-to-end test suite. And that's basically where this 51 peg data came from, that I'm showing in the top right here. Is we collected this, and at our sensitivity, 51 peg is quiet enough and well behaved enough that we can use it as a star, or as a canonical metric to make sure that our pipeline is not doing something silly. So I think you're exactly right. You hit it on the head that we need to come up with a super quiet star with data that is processed, and it probably going to be manually processed to begin with, to say this is the right answer. And then you, as part of the end-to-end tests, which only get run up, by the way, when you're trying to pull in like a full new pull request. It's not going to be every time you change like one little bit of the code. But when you're talking about actually you've done your whole change, you change your whole algorithm, it's then going to run the full end-to-end test suite. And that's where you can start to say, okay, the RMS better be at this level, or you have to, pick your favorite metric. If you want to say, look, the RMS has to go down, and this is the absolute value that it has to be, or something like that, you can add all of those into your test suite. Yeah. Eric.
I'm curious about, you present sort of a functional interface to deal with connecting things. An alternative is sort of a file-based system where you define checkpoints at files so that different pipelines know what to accept as inputs and outputs. And that would maybe free people from having to glue their code into your framework or your code into their framework. And I worry that as tempting as it is to say, hey, everybody, why don't you use my framework? From experience, it often doesn't happen. And so I'm wondering if you've thought about some of the pros and cons or challenges of a file-based approach.
Yeah, so for us, we thought about this very early on, because being a network of telescopes, we have 25 of these different telescopes we're dealing with. and operating in the cloud, doing file point checkpoints was just going to be prohibitive from day one. It, when you're talking about, say, cloud storage, for example, you don't just store things to disk, you store them to S3 objects. And so, having to send things back and forth to the bucket was just going to be not performant enough for what we wanted. And so in that case, that's one of the reasons that we have chosen in our internal bits of the framework to only be things, to just pass from stage to stage to stage. That being said, it's very easy to use Banzai to just only do one stage on something and write it to disk, and then only do the next stage on something and write it to disk as well. You just have to change the philosophy a little bit on how you're writing really just that list of stages. But in general, it's very possible to do.
But I guess I'm thinking if Banzai and the JPL pipeline and the Geneva pipeline, if we kind of could agree, we'll write a version of our L2 product that meets these specifications, then everybody who wants to use any one of those 4 pipelines outputs would know not only could you write out the stuff to disk, but it would be stored in a similar way so that I can read and pick up and run with it. So I think it would require a little bit of thinking and coordination, not just, every code can dump what it's doing, but figure out what everybody wants and what would need to be. So it might be a little more challenging than it first seems.
Yeah. So absolutely. It is very challenging. Unfortunately, the psychology and sociology of that problem is a lot harder than the actual technical side, or the political, whatever, fill in the blank. But let me see if I can go back to this real quick. We've basically done a version of that in this style of setting. So you don't have to change anything else you're doing. You simply say, okay, this is the format that maps from here to some agreed upon middle format, which in this case, I'm just using Banzai. And then, again, Banzai can evolve to the needs of whatever it's doing. It's not set in stone. That's the other nice thing about being open source, is that I really do want to encourage public contributions and have other people working on it. And if we find it doesn't meet the thing, we change it. It's like, that's the beauty of it. But by having this kind of intermediate data structure, you can say, okay, this person has defined their output to look like this. You just write the mapping down into a file like this, and then Banzai can pick it up and process it however you want. And you can say, then convert, say, the output of one pipeline, as long as you've written the mapping down, into, comparisons with another one.
I will take this moment to plug the fact that there's a group right now working on a standardized data format for EPRV data at the 1D order by order spectra level. So that's where we're starting. This is actually the talk that Curtis saw at SPIE that prompted our conversation. And so we've got representatives from, I think, every EPRV group involved at the moment, and we're slowly working towards consensus on what that looks like. And then it'll be presented to the community, hopefully in a few months' time. But that one of the things we're thinking about is then going from the, as the instrument provides the 1D order by order spectra, to then all the post-processing things, and the idea that if everyone's in a standardized format, then it becomes a lot easier to apply any of those post-processing steps across instruments in a way that doesn't require bespoke pipelines.
Yeah, and I'll also make the statement that one of the things I've found, even comparing Banzai with, Pipette or some of these other pipeline frameworks out there, is that it is surprisingly hard to separate into most pipelines, including Banzai at times, into testable chunks. And it's amazing how much weird interdependences there is between the different pieces of the pipeline. And so it is significant work to be able to do an apples to apples comparison, because you have to actually separate the part of the logic that you're trying to test. And that's non-trivial. But it also is helpful, I think, in the long term when you're talking about trying to beat down systematics, because if there's secret sauce that is happening somewhere else that's not in that bit of your algorithm, you want to know about it. And so I think it's effort well spent, but it's definitely effort you're going to have to do comparisons.
Yeah, absolutely. Curtis, I want to be respectful of your time because I think you need to run off and lead another meeting now. Is that true?
Yeah. But yeah, no, send me an email. I'd love to talk more to people. Again, if we can be Switzerland in this kind of thing, that I mean, we don't really have like instrument skin in the game on trying to get down to 10 centimeters a second. So if we can kind of work as like a middle comparison spot for some of these pipelines, that'd be really great. So.
Excellent. Thank you again so much for a wonderful presentation. Thank you all for calling in. And again, we'll see you next month on September 26th for Danny Krolikowski's Colloquium on Tellurics. So take care until then, folks.